of load on a cooling tower if the entering and leaving temperature are 96 and 88 degrees Fahrenheit respectively, and the flow rate of the water over the tower is 30 gallons per minute. So the load on a cooling tower is equivalent to mCp delta. Okay, so Cp is our specific heat, which is a constant, and we have the exit and entrance temperature of our cooling tower, so we can solve our change temperature. But M is the mass, and as we can see, what we do have here is the volume flow rate. But we know mass and volume is related through density, which is mass over volume, meaning mass is density times volume. So meaning we can solve our Q directly. So our Q is equivalent to mass, which is density times volume. Okay, so for our density, we can use the value 8.33, which has a unit of pounds per gallon. So this is very helpful if our volume has a unit of gallons, which is true in this case, which is 30 gallons per minute. Cancel. So we have the mass. Sieve of water in the English unit is 1 BTU per pound Rankine. And the change of temperature, that is 96 minus 88. That's change in Fahrenheit, which is also the change in Rankine. So our load is in BTU per minute. What is our load in the cooling tower? That is equivalent to 1,999.2 BTU per minute. So the best answer is 2,000 BTU per minute. The changing of solid directly to vapor without passing through the liquid state is called sublimation. Our rectangular duct has a dimension of 0.25 meter by 1 meter. Determine the equivalent diameter of the duct. So from the ducting's lecture video, we know that the equivalent diameter given the dimension of a rectangle is equivalent to 2AB over A plus B, where A and B are the dimensions. So the equivalent diameter is 2 times A. So let's use the first dimension as 0.25. And B is the second dimension, 1 over A plus B. What is the equivalent diameter? So that is 0.4 meters. The changing of a liquid passing a cross-section of a stream in unit time is called discharge. A sudden enlargement in a circular duct measures 0.20 meters diameter upstream and 0.40 meters downstream. The upstream pressure is 150 Pascal, downstream pressure is 200 Pascal. What is the flow rate of 20 degrees Celsius air through the fitting? Use density of air as 1.2041 kilograms per cubic meter. Okay, so we are asked here to find the volume flow rate of the 20 degrees Celsius air. So we know if the dimensions of a circular duct is given, the formula for the volume flow rate is area times velocity. Okay, so since we have the diameter, we can solve our area. So meaning we should find the velocity. So if, as you can see, we have here a sudden enlargement on our ductings. So for a sudden enlargement of ductings, there must be a pressure loss along our flow of air. So using the conservation of energy in the upstream and on the downstream, we have a derived formula for the pressure loss due to the sudden enlargement. So that's equivalent to V1 squared rho over 2, quantity 1 minus area 1 over area 2, quantity squared. Take note, point 1 denotes as our upstream and point 2 is our downstream point. Okay, so our pressure loss is the loss of our pressure in the upstream and in the downstream. Okay, so as we can see here, our unknown velocity is right here. So we can solve our V by using this formula. Okay, so let's identify our givens here. Okay, for our pressure loss, this is the difference of our pressure in our upstream and in our downstream. Okay, in the upstream, we have 150 Pascal. And on the downstream, we have 200 Pascal. So our pressure loss is 200 minus 1T is equal to V1 squared times rho, or our density, 1.204 over 2. Quantity 1 minus our area 1 is the area of our cross section for the circular duct, so that will be pi over 4 diameter squared over the cross section area downstream, so that will be pi over 4 diameter squared. Then do not forget our exponent here. So we can cancel out pi over 4. So calculating, our V1 is equivalent to, this is equivalent to 12.15 meter per second. So we have the value of our V1, meaning if you are to use V1, our area should be also at point 1. Okay, our volume flow rate is area 1. It is the area of our circular duct at the upstream. So that will be pi over 4 times the diameter upstream. That is 0.20 squared multiplied by V1, which is 12.15 meter per second. What is our volume flow rate? It is equivalent to 0.38 meters cubed per second. Next one. If the volume of the confined gas is constant, the pressure is directly proportional to the absolute temperature. It's known that Charles law. 27. Determine the heat extracted from 2,000 kilograms of water from 25 degrees Celsius to ice at negative 10 degrees Celsius. So we have here heat extraction from water to transform this into ice. So first, we must bring the water to its freezing point, and then we can now change the phase from water to ice, and then we can further lower the temperature of ice to the desired temperature. So this is actually a combination of sensible and latent heat. Our formula in this problem is M times the quantity of Cp of water times the change of temperature of water plus the latent heat of fusion plus Cp of ice times change of temperature of ice. Okay, our Q is equivalent to M is 2,000 kilograms multiplied by the Cp of water is 4.187. Our change of temperature, so initial temperature of the water is 25, and it will be lowered to the freezing point, which is 0, plus the latent heat of fusion, which is a constant, is 335, plus the Cp of ice, which is half of 4.27, and that's 2.0935. That's the change of temperature of ice. So initially we are at the freezing point, minus negative. So inside of our bracket, the unit is kilojoules per kilogram. So we can cancel out kilogram. The heat extracted in kilojoules is 921,000 220 kilojoules. Next one, the temperature of a confined gas is constant. The product of the pressure and volume is constant. It is also known as the Boyle's law. Number 29, in an ammonia condensing machine, which has a compressor plus condenser, the water used for condensing is 55 degrees Fahrenheit, and for the evaporator is at 15 degrees Fahrenheit. Calculate the ideal coefficient of performance. So take note, COP, if the temperature limits are given, it is equivalent to T low over T high minus T low. Take note that temperatures must be expressed in Rankine if we are talking about English units. So T low, obviously, is the lower one, that's 15. So we must add 460 to make this Rankine. Divided by T high minus T low. Okay, should we add 460 on both T high and T low? Actually, we can skip that part because the change in temperature on the Fahrenheit is also equivalent to the change in temperature in Rankine. So, meaning in the denominator, we can neglect the part where we add 460. So we could just directly get the difference of the T high, which is 55, obviously, and then minus the lower one, which is 50. So that is change in Fahrenheit, which is also change in Rankine. Cancel. What is the COP? This is 11.875. What is a force which tends to draw a body toward the center about which it is rotating? It is called the centripetal force.